сегодняшняя лекция у нас будет такая вопрос о том, зачем это все нужно. Она будет как бы про группы Ли и про алгебру Ли для тех, кто ничего не знает ни про группы Ли, ни про алгебру Ли. И я надеюсь, самое главное, что у нас будет, это пример, который мы разберем, понять, как это все вообще связано с тем, что мы делали до этого. Вот. То есть я так посчитала, раз у нас будет потом зачетная неделя, когда видимо, мы поговорим про вот это все, потом немножко поговорим про представление, и уже тогда со следующего модуля начнем заниматься группами отражений. Вот. Ну что? Ну, пока по-русски, но на всякий случай напишу по-английски. Вот, значит, что такое группа Ли? Группа Ли, у нас все будет комплексно, я не буду ни вещественными, ни тем более вторичными полями я заниматься не хочу. Значит, группа Ли, во-первых, это должна быть группа. Что такое группа? Все же помнят, да? Вот, значит, но при этом она должна являться сама по себе как множество классным многообразием. И еще мы потребуем, но это не сильно будет сложно. Вот у нас есть операция μ умножения. Умножение μ, которое берет x, y, два элемента нашей группы, приводит к произведению x, y. Еще взятие обратного. Я возьму такой странной буквой I. То есть оно x переводит в x минус 1. Эти два отображения должны быть дифференцированы. Эти два отображения пример. Здесь такой пример, которого у нас потом не будет. Пример такой. ЖН. Все помнят, да, что такое ЖН? Матрицы, у которых определитель не 0. ЖН, матрица. Что мы имеем? Что такое μ? Мы берем, я не знаю, там матрицу А, матрицу Б. Получим какую-то матрицу новую, да? У нее и каждый элемент задается какой формулой? Сумма чего-то А и житая, Б жкатая. Это маленькие буквы напишу тут. Здесь напишу маленькие. А и житая, Б жкатая. Ну, то есть, что мы имеем? У нас умножение μ будет n квадрат компонент, и любую компоненту, если мы будем дифференцировать там по a-шкам или по b-шкам, у нас все получится. То есть, вот это вот штуковина дифференцируема по всем а и житая, там, b жкатым. Ну, просто будет какая-то линейная функция, мы ее продифференцируем, получим чиселки. Вот, как на мотане. Чуть-чуть сложнее с обратным. Если мы берем а минус 1 какой-нибудь изжитое. Как мы умеем обращать матрицы? Обратная матрица как напишем.
Сейчас. Ну, в теории надо присоединенную брать. Да?
Да, вот здесь удобнее через присоединенную. Была матрица А.
Это очень сложно, но придется, видимо.
Да, мы же не будем честно писать. Нам надо все равно верифицируемо. Нам надо вычеркнуть вот эту вжитую строку итый столбец. Останется матрица, которая алгебраическое дополнение к элементу ЖИ. Мы должны посчитать ее определитель. Было дело. Вот. Ну, это будет какой-то где-то, я напишу, ажитое, алгебраическое дополнение. И еще надо поделить было на определитель всей матрицы. Ну вот, мы, в общем-то, не особо интересуемся этой формулой. Нам важно, чтобы оно было дифференцируемо. Ну, вот попробуем продифференцировать по какой-то переменной. Вот дифференцируем по, я не знаю, там буковке А и Ж, да? Как мы дифференцируем частное? У штриховой минус у v штрих делить на v квадрат. То есть вот здесь мы напишем квадрат, а здесь, ну, вот этот определитель мы как-то продифференцируем по А и Ж тому, и что-то мы нормально получим многочлен. I'm sorry, just I started in Russian, just I defined what is a Lie group. Do you know the definition of a Lie group? Yes. Okay, so the only thing that we've done is the definition of a Lie group. Вопросы? Мы не будем особо этим заниматься. Нам надо более-менее. Хорошо. Дальше что? Okay, so now I continue in English. I want to define what is a Lie algebra. Just I take, so this is my group G. We have the identity element. And we can take the tangent space. Just as of a manifold. And in fact, there is almost a bijection between Lie groups and Lie algebras. Up to connectedness and simple connectedness. I can draw a real picture. Okay? For 5 minutes, we will have Lie groups of real numbers. For example, this is a Lie group. Okay, with plus. Its tangent space in the identity is also R. Okay, then I can take another one. I can take 5 modulo 2 pi. So I can sum up 2 angles and also obtain an angle. This is the identity element. What is its tangent space? It is also R. So for these two Lie groups, the Lie algebras are isomorphic, but they have very much in common because it is not simply connected, and this is its cover, simply connected cover. Еще раз, вот это будет односвязанная накрывающая вот этой штуки. So up to some
quotient, which is discrete in this group, they are identical. And also,
what if our Lie group is not connected? For example, we can take 2 copies of this one. Just take a product with any finite group. Then the tangent space in identity will remain the same. Up to these 2 obstacles, Lie algebra knows everything about the Lie group. Okay, I didn't say about the commutator in the Lie algebra. I should define it. Just for each element of the tangent space, we can take a curve in the Lie group for which it is a tangent vector. Okay? So if x, so we denote Lie algebra by a factor of letter G. Schrift das Fraktur. Not factor. Okay, so suppose that x is in our Lie algebra, and this is the curve AS. It is a smooth curve in the group. And then let us take another vector y from the Lie algebra. In the Lie algebra, T, another curve in G. So this will be some curve in our group. By construction, this is the identity element. So when T or S equals 0, they should pass through the identity element. Две кривые в группе, проходящие через единичный элемент.
So, do you remember what operation should we have in a Lie algebra? Какая должна быть операция в алгебре Lie? Yeah, so we need to define what is the Lie bracket xy. So it is defined as follows. We just write down the group commutator. The group commutator will be A, S, B, T, A minus 1S, B minus 1T. And then we need to differentiate it at 0. This will be d dt so this gives us an operation which behaves very well. So what are the properties of these of this Lie bracket? Properties, we will not check them, but it will follow easily just from this definition. So subgroup in J, it will correspond to subalgebra in the corresponding Lie algebra. For example,
in GMS, we have a special linear group SLN of matrices with determinant 1. It corresponds to the subalgebra of all matrices with zero trace. So for GLN, it has dimension n squared, and its tangent space has dimension n squared. So the Lie algebra tangent to GLN is all the matrices and of dimension n squared. And if we take SLN in GLN, we take all the matrices with trace 0.
So a normal subgroup it will correspond to ideals in G. So an ideal is that if you take an element from this ideal and commute with any element from G, you remain in the ideal. In fact, SLN in GLN is an ideal, since for any commutator the trace is 0. Понятно? So what is an ideal? This is an ideal here. If you commute an element from here and from here, and you still remain in the smaller one. If you commute two matrices, you get a matrix with 0 trace. So in fact, matrices with 0 trace, it is an ideal in the set of all matrices. Okay. Да.
Wouldn't it be also subalgebra? But it's also subalgebra.
Yes, definitely. Definitely.
Not
And
easy to understand.
Yeah. It is
Difference.
ideal is more strict than a subalgebra. For H, if you want H in G to be a subalgebra, you need that two elements from. If you take x, y from H, you need the commutator be from H. And if you define an ideal, you take x from H and y from G. And you still require the commutator to belong to H.
Okay, subalgebra is ideal, but ideal.
No, an ideal is a subalgebra, but not any subalgebra is an ideal. If you...
Yes, because when we have ideal, we have more условий.
More conditions, yes. For example, the upper triangular matrices, it will be a subalgebra, but not an ideal. Upper triangular matrices. If you take non-zero elements here and 0 here, it will be a subalgebra, but not an ideal. Just if you commute two upper triangular matrices, they remain upper triangular. But if you want to commute them with some other matrices, they will come out from this set. Just Eij, Ejk gives you Eik. So no need to be upper triangular for an appropriate choice of K. Okay.
Сейчас как-то алгебра Ли, это вот касательно пространства в единице.
Да. У которого коммутатор пришел из умножения в группе. Еще раз, я сказала, что если мы берем, во-первых, несвязную группу, то мы ничего не знаем про структуру на компонентах связности, алгебрари про это не знает просто. И еще мы не знаем, если мы подфакторизуем группу по дискретной подгруппе. Но в сущности до этого алгебрари знает все про группу. So there is this theorem that if you take the exponential map, then you can reconstruct a connected, simply connected Lie group from its Lie algebra. But this is not the topic of today's lecture. Just I mentioned that there is a bijection between Lie algebras and connected, simply connected Lie groups. Okay, and so why do we need root systems? They're very useful for classifying Lie algebras. So the aim is to classify all Lie algebras. So in some sense, there are two opposite situations. A Lie algebra can be either semi-simple. Semi-simple, it means that it has a non-degenerate invariant scalar product. And at the other pole we have solvable. So these are more easy to classify. We are not going to talk about this. The most hard part when you want to classify Lie algebras is to classify semi-simple Lie algebras. Полупростые алгебры. So when you have a non-degenerate scalar product, then you say that your Lie algebra is called semi-simple, and this is our plan for today, to talk about this on the examples. So maybe should I start with a special linear group and its algebra, or we can discuss the orthogonal group? I think I will start with the special linear group. How do we understand that y as n, the tangent algebra to the group SLN, is defined by trace equals 0. I will write it down. What is the condition? So this is take x. It is tangent to some curve in the group SLN. So this is our group SLN. This is the identity element. And suppose that there is a curve. What does it mean, a curve? A curve, it is a set of matrices. I want to write it in the following way. This will be 1 plus A11P
A130, etc. One plus
This is matrix, yes?
yes, this is the matrix which gives the point AT, point of the curve. AT. That is it here. Okay? So, my aim is to say that let Aij 0 be equal to 0. The condition that this curve passes through the identity is that if we put 0 everywhere, we get 1, 0, 0. So all of my functions will be 0 and 0. And what is our condition? It is that the determinant equals 0. Let us write it down. The determinant of this matrix equals identically 1. Okay. I hope you remember the formula for the determinant. And now my aim is to expand it totally in mind and then differentiate by t and put t equals 0. Помните формулу для Okay. Maybe...
Так, она же не верхний треугольник тут.
Чего? Не, здесь что было, давайте. Okay. For example, what happens if I multiply these two terms? If I multiply this and this, then I differentiate it by t, and then I put t equals 0. What will happen? You take a1 to t, a to 1t. If my product contains, for example, two terms, if I differentiate by t, and then put t equals 0 of this stuff, it will be a1 to prime t, a to 1, plus a1 to t, a to 1 prime t. Okay? And when I put t equals 0 of this stuff, this will vanish, and this will vanish, and everything will vanish. So if we have a product of two functions which vanish at 0, they will not enter in this stuff. So if I say that the determinant is identically 1, then I can take d over dt and put t equals 0. And if I take it here, it will be 0. And it will be our condition on the matrix from its tangent space.
Почему 1 плюс что-то не рассматривали?
Сейчас, давайте мы разложим какие-то.
this is not a final answer. I just say that if we write down this determinant, differentiated by t and put t equals 0, then we will get 0. Because we differentiate the constant and we obtain 0. What is this determinant? It will be one term which is the product of the diagonal elements. It will be 1 plus a11 plus a22 plus etc. plus a_n and plus that doesn't matter. Plus the terms which will not matter. Why? So if we take the product of the diagonal elements, it will start with this, and then we will take pairwise products, and then we have triple products, etc. And if we skip some elements of the diagonal, we cannot skip only one element of the diagonal. If we skip two elements of the diagonal, we obtain two elements of this kind. And it will not matter in the answer. Мы не можем проигнорировать один элемент на диагонали. Мы можем только два проигнорировать. Возьмем два элемента вот так, и они войдут во втором порядке. Будет вот так 0. So if we differentiate it by t, it will not play a role. We will have plus a22. It will be equal to 0. So this will be our condition for the matrix to be in the tangent space to SLF. So its tangent space is defined by the condition trace equals 0. So we have constructed this Lie algebra by hand. Now I want to...
Там у нас вот с N лежат как бы, матрицы, элементы матрицы дифференцируют.
Да. У нас все гладко, многообразие гладко, все элементы дифференцируют. Кривые гладко.
И сейчас мы рассматриваем матрицу исходная с N.
Да. Нет, сейчас это была кривая через две проходящие. Do you understand what happens? Okay. Так,
I
давайте.
don't understand the last step.
If you understand, I will just explain in Russian what happens. Еще раз, какие вопросы по этому?
Я концептуально не понял. Мы взяли кривую,
Да.
продифференцировали ее
Да, в
в
группе.
нуле
Да.
и показали, что след элементов на производных элементов на диагонали это 0.
Ну, в смысле, сейчас скажу. Как бы это кривая в группе. В принципе, касательный вектор к этой кривой, это что будет? Это будет вот это вот со штрихом, вот это со штрихом по t при t равном 0. Единичка уйдет.
Короче, все элементы продифференцировались.
Да, это будет касательный
Вот
вектор к этой кривой.
Вот мы показали. И вот SLN алгебра Ли у нас состоит из касательных векторов.
Да.
Вот мы показали, что все касательные вектора у них след хорошо.
Да, потому что мы кривую брали не где попало в группе, а в группе там есть какие-то ограничения, конкретное ограничение, что определитель равен 1. И если мы это ограничение дифференцируем, мы как раз получаем условия на след.
А как мы определитель раскладывали для того, чтобы прийти?
Чего?
А как мы тут,
Стоп. Формула. Это сумма по всем ладейным расстановкам. Да, что такое ладейная расстановка? Выбрать надо n клеточек, никакие две не в одном строке, в одном столбце. Из ладейной расстановки следует, что мы не можем взять n-1 клеточку на диагонали и одну где-то еще. Мы можем взять n-2 клеточки на диагонали и две где-то еще. Или хуже. Yeah, so in the other direction, if you take the exponential map to construct the Lie group from the Lie algebra, this condition that trace 0 will give you that the determinant will be equal to 1. But it is not for today. Okay, this was the basic example. How do we obtain a special linear, how do we obtain a Lie algebra from the special linear group? I want one more example, and then I will say some terms about Lie algebras. Another example is what? Do you know what is the orthogonal group?
DN, right? Orthogonal group means DN.
It will be DN, yes.
Okay.
Just 2 papers and it will be DN. Orthogonальный матрицы как раз определяется. Супер. Теперь будет распределение произведения чуть-чуть кривое. Okay, what is, so we treat right now the special orthogonal group of dimension 2n.
Special это то, что как видите.
Да. Yes, I write the determinant equal to 1 because in fact, if you take the orthogonal 1, its determinant can be either plus 1 or minus 1. So it is a classical example of a group which is not connected. You have 2 copies of some stuff, so the identity lives here. You have no identity matrix here. And so its tangent space, it will be the same for this one and for 2 copies of it. So for this, if we want to work only with connected groups, we don't take all the ON, we take only SO. It preserves a scalar product, so asymmetric bilinear form. So for our simplicity, for our formulas, it will preserve the following symmetric bilinear. It will preserve so it will be of size 2n by 2n. So it is symmetric. If you reflect it, it will be symmetric. It will be bilinear. It will be non-degenerate. Its determinant is plus minus 1. So it is a good way to define orthogonal group. It is allowed. So the question is, what is its tangent algebra? My plan was to make this calculation to show that everything can be done in an honest way. Let us find its tangent space. We know that it is P plus A, B. So it has, we split into n by n blocks. C,
B, one identity plus, as at the previous slide, A, B, C, and D, these are matrices which vanish at 0. So this is a curve of passing through identity. Okay? Alright. E 0 0 E. This is a 2 by 10 by 10 matrix, and this is also a 10 by 10 matrix. Okay? And what does it mean that it preserves this bilinear form? We multiply it by 0, and we take its transpose. So if we act on vectors, then the scalar product, they change in the following way: E plus transpose. I'm very sorry, there are two different keys, one for transpose and one for the parameter. But I hope it will not.
You can use capital T for transpose. You can just use capital T for transpose.
Yeah, okay, I will do this. This will be for the transpose. Transpose. No need to transpose the identity matrix. And if we transpose, B goes here and C goes here. C, T, and E plus B transpose. It should be equal to this bilinear form. And then we will also differentiate it by t and take t equals 0. I want to write down this condition. First I multiply these two matrices. I obtain B identity plus A identity plus D, and then C. I need to multiply with E plus A transpose C transpose B transpose and identity plus D transpose. When I differentiate this, I obtain 0.
Это напрямую то, что слева.
Да, пока что мы просто пишем то, что слева. Пока что оно равно.
Я думал, вы просто собираетесь дифференцировать равно.
Сейчас придифференцируем.
Пока просто не
Я хочу, чтобы мы не запутались. Now let us take d dt and then t equals 0. And d dt and t equals 0, it will be 0. What if we expand this? If we expand this, I want to multiply it in my mind. So it will contain bt plus bt a transpose t. I write it like somewhere. So you see, if I multiply this with this, bt times e plus bt times a transpose
T. So this will vanish. Since T enters twice, but we differentiate once, then we put T equals 0, the second part vanishes. Еще раз, степень вхождения T сюда как бы 2. Мы дифференцируем произведение, потом повторяем T равно нулю, и вот это все оба слагаемых у нас занулятся.
То, что след, ну,
Да, вот сейчас я хочу, когда буду это умножать, сразу часть членов не писать. So, I want to say the
можно не
difference.
все.
Сейчас.
So we don't write products of more than two somethings which are depend on the, yes?
Сейчас, let me rewrite it. This will be equal to d dt for t equals 0. I write the product, but I omit terms of this type. The remaining is bt plus b transpose t. Then for this one, btct will vanish, e times e will vanish. We obtain a plus d transpose. Once more, I should have here btc transpose t plus 4 terms coming from here. But the identity times identity gives 0. A times d transpose gives 0. Понятно? Там бы было 5 слагаемых, но я оставила только 2. Okay, now for this term. We have A transpose plus D, and all the other stuff will give 0. D times A transpose, C times B transpose, they will give 0. And the last one, we have C transpose plus C. So this times this C transpose, and from this product we keep C. Equals 0. We are almost done. How should I write this? Suppose that A, B, C, D, it is an element of the tangent space, so to N. So A is of A, and so on. What is the condition? It is B plus B transpose, which is 0. A plus D transpose, it is 0. This is the transpose of this one. And C plus C transpose, it is 0. So, this matrix is skew-symmetric. This one also is skew-symmetric. This matrix is arbitrary, but this one is defined by this one. You choose any A, you choose skew-symmetric B and C, and you have defined your matrix.
Что так сложно?
Сейчас, подождите, сейчас будет ДН. Я не хочу писать абстрактные формулы, я хочу, чтобы формулы были более конкретные. Поэтому... Do you remember what happened there?
Maybe I copied this. A plus B transpose equals 0. B C to choose an abelian subalgebra. So a subalgebra on which the commutator vanishes. Do we have diagonal matrices here?
Yes. Ой, ну,
Есть ли такие штуки диагональные матрицы?
Да.
Да.
По и С берем кривые,
Так.
А берем диагонально, тогда и диагонально.
Yes. So it has a subalgebra of x1 etc. on the diagonal minus x1 etc. minus xn. So if we take the commutator, it is 0 on this subalgebra.
This is H. Okay. Do you see that the commutator is 0?
ништяк, кстати.
Yeah.
Just what is the commutator on the matrices? We write the matrix product with some y1 minus y1 x1 etc. So just on the diagonal you have the products of xi, yi. Then we subtract them and it vanishes. Okay. So this is an abelian subalgebra. If we want to construct
A root system, it will appear soon. How does H commute with all the other elements? What is this is the question.
Просто перемотаем.
Нет, в смысле, H with H gives 0.
Yes.
But what if we commute H with all these algebra?
Ну, тоже нет. Нет. Там же будет произведение элементов на диагоналях минус произведение элементов.
Сейчас, у меня все полстранички текста. Сейчас мы победим. Сейчас мы получим D. Okay. What basis can we take in this algebra? First of all, we have the diagonal matrices. It is the subspace of dimension n. I will not choose a basis there. It is nice enough. But now I want to take for example, we can take 0, 0, 0 and some skew symmetric matrix here. So it will be E I n plus j minus E j n plus I. I is not j. Okay.
Что это мы написали?
Какая-то матрица, которая сидит в нашей алгебре. Мне нужно построить в моей алгебре базис векторного пространства.
Если вот эту матрицу вот так записать.
Да. So this matrix, which has something non-zero on B place, and which has 1, 1 and 1 minus 1 on B place. It would be Eij minus Ej I, but we shift it on the right. That's why we have n plus j and n plus I. So this is n plus I. We will also have stuff with plus 1 and minus 1 here.
And also we will have something like this. EIJ here and EIJ minus EN plus J N plus I. Okay. What if I compute the diagonal x1 etc. xn minus x1 minus xn. This is an arbitrary element from H. I compute it with, for example, this stuff. E I n plus j minus e j n plus I. So we multiply this by this. Xi gives no zero with this. E I n plus j minus x, no, plus xj will work here. Xj e j n plus I. Do you understand? Еще раз. Смотрите, вот это у нас было как бы E11, XN, ENN. Да? Как у нас маточные единицы умножаются? Если они не зацепились, будет 0. То есть вот с этой матрицей зацепится только EII, вылезет число XI, а все остальные умрут. Опять же, с этой матрицей зацепится только EJJ, вылезет XJ. Когда мы будем в обратном порядке домножать, будет с номером n плюс j будет минус xj. So, if we subtract, we will subtract minus xj e I n plus j, this with e number n plus j, and minus x I. How many times should I take minus? Minus e j n plus I. So in fact this should give us, I checked myself, xi.
Все, что ли, объяснил, да?
Да, все остальные умерли.
Сейчас это не только как можно в одном порядке.
This is the first direction, and this is the second direction.
Так, что он должен зацепиться и там, и там.
This will be minus e I n plus j minus e j n plus I. Just I omit the first half. Minus x1 e n plus 1 n plus 1 minus xn e to n. Okay? I don't rewrite the first half, it will vanish. Then I seek n plus j here, minus xj e n plus j n plus j. This with this will give us not zero. Here it is. And for this, I seek for xi, e n plus I, n plus I. And that's all. So we obtain e I n plus j minus e j n plus I. So in fact, this is an eigenvector, and this is our eigenvalue. This is our eigenvector. You can check it yourself. Just matrix products. One more check. Maybe I have not enough time. I just write it down, but it is the same check. This is just the basic algebra. If I can use the same diagonal matrix. With this stuff. Ej minus en plus j n plus I will obtain xi minus xj times this vector eij minus n plus j n plus I. Do you believe me?
Yes.
What in total? What is the set of eigenvalues? The set it will be xi plus xj. So in fact minus xi minus xj if I take 1 minus 1 here and xi minus xj. What does it resemble? На что это похоже?
На систему корней.
На какую?
На плюс-минус литр, плюс-минус ложитр.
Да.
Е8.
Нет. What root system did you obtain?
Ден.
Yeah, yeah. This is dn. Now I want to say a few words about Lie algebras in general. So do you remember what happened? We have something diagonal. If it is diagonal, then it is easy to check that commutator is 0. What if we have a semi-simple Lie algebra G? Then we take H, the maximal abelian subalgebra. For example, if we take a one-dimensional subalgebra, it will be always abelian, x commuted with x is 0. If we can extend it to another subalgebra with 0 commutator, then we do it. If not, we stop. By the dimension reasons, it exists. Maximal with respect to inclusion subalgebra such that the commutator is 0. In fact, we can act by act by all elements of our subalgebra on our Lie algebra. H commuted with X. It is a linear operator. On G. Okay? Just it is linear. So it is a linear operator.
But now, in fact, we have many linear operators acting on our Lie algebra, and they all commute. Why? I can write the Jacobi identity. Do you remember the Jacobi identity?
Да.
So what is the Jacobi identity if I take H1 and H2 from our Cartan subalgebra? It is called Cartan subalgebra. H1, H2, X. We have it in the seminar.
Можешь выбрать такая simple, максимально.
No. Semi-simple is the algebra on which we have a non-generate scalar product. In fact, it is a non-general, non-degenerate G-invariant scalar product. I didn't define what is G-equivariant, but in fact, if you remember, for our root system, we've had a Euclidean space. So there was a scalar product. In this setting, the scalar product on G will be necessary to define our root system. So the Jacobi identity, H2 x H1 plus the third term, it will be x H1 H2. It will be equal to 0. But what can I say about the third term?
It's 0.
Yes, it's 0. H is a billion.
Inside is 0.
This is 0 since H is a billion. So this term vanishes. And we know that commutator is, so if we switch these two elements, minus comes out. So we obtain that H1 H2x equals H2 H1x. So this infinite set of operators can be diagonalized simultaneously. I didn't mention that they are all semi-simple, but it is true. So it contains
So all the matrices will be diagonal. So will be so the operators which correspond to this commutator, they will not have Jordan blocks. It can be proved together with the fact that it is a billion. Операторы бывают полупростые и нипотентные. Полупростые — это те, которые в каком-то вазе диагонализуются. А нипотентные — это те, которые в какой-то степени замеряются. Еще раз, вот из этого свойства следует, что на самом деле все эти операторы, которые H с кем-то коммутируют, они будут полупростые. Я не буду в это сейчас вдаваться, но это прям проверка.
Полупростые, то есть где-то диагонализуются.
Да, где-то диагонализуются. Ananya? I just said that all the operators corresponding to these commutators, they will be all semi-simple. So diagonalizable in some basis. this is in bunch with the maximal abelian. Usually it is defined as the maximal subalgebra consisting of semi-simple operators, and then people prove that in fact it is abelian. Okay. Okay, our aim was to classify all the Lie algebras. We are very close to root systems. So, what about our Lie algebra? We can decompose it into the eigenspaces. So, clearly, if we diagonalize simultaneously all operators when we commute h's with something, in fact it is other h. I mean, this is a linear operator which takes x and gives you the commutator of h and x. If we diagonalize them, we say that G is the direct sum of eigenspaces. We've had it on the example. In fact, it is h on which it is eigenvalue 0 plus the direct sum h in this with alpha. Oh no, g. In fact, alpha, they live in the dual space. We've had the example. We can compare this identity with our example. What was our SO to N?
What is GF?
This is the eigenspace. Eigenspace. So we have an infinite number of operators. Each has its own eigenvalue. Do you remember that we've had some eigenvalues of kind xi plus xj. In fact, this is a linear function on h. So if we sum up two elements, then the eigenvalue which will come out, it will be the sum of eigenvalue corresponding to one and to the other one. So we have some matrices 1 minus 1, and we have 0, 1 minus 1. The sum will be 1, 0, minus 1. One has eigenvalue x1 plus x2, the other has x1 minus x2, x2 minus x3, and the sum will give x1 minus x3. So this is the decomposition. Any semi-simple Lie algebra has such a decomposition. And it is not difficult to check that. So for simplicity, we also sometimes say that this is G0. If in the Lie algebra you commute G alpha and G beta, you will be in G alpha plus beta. You also can check this using the Jacobi identity.
How can we obtain it from the Jacobi identity? If we take x from here and y from here, we want to find what is h x y. H is an arbitrary element from the Cartan subalgebra. I write in this form: plus x y h plus y this it equals 0. Okay, this is what we are seeking for. This is if we take hy, it is beta as a linear function calculated in h times y, and minus 6 we have to transpose them. So this is some number. This is some number. This is a vector. Okay, and here we have a minus alpha times our vector. This is a number, this is a vector. So, no, not minus, plus, yeah, plus. All in total, we have that our question, we have that h commuted with the commutated xy is beta plus alpha. This is some number times the vector commutator of x and y. But this means that xy lives in the eigenspace with the eigenvalue beta plus alpha. This is beta. Should I explain once more?
Что-то вообще не понял, что произошло.
Ну, для этого я был пример. Мне нравится вот так, вот давайте на примере разбираться.
Что мы вообще сделали?
Разложили ангелы в тривиальном собственном пространстве. Okay, let me come back. So this was our Lie algebra of dimension something like 2n square or something like this. Okay, it has an n-dimensional subspace here, and also it has many vectors which are eigenvectors for the action of h. So this is an eigenvector with eigenvalue xi plus xj. This is an eigenvector with eigenvalue xi minus xj. And in fact, if we commute to these matrices, we will need to sum up the eigenvalues. And if we take, for example, x1 plus x2, x1 plus x3, their commutator will be a vector with eigenvalue to x1 plus x2 plus x3. But we don't have such a vector in our root system. So that commutator will vanish. So in fact, we have decomposed our Lie algebra as O2n is in fact the direct sum of h plus the sum alpha equals plus minus xi plus minus xj of one-dimensional subspaces g alpha. Okay? In such a way that if we compute G alpha and G beta, you will move to G alpha plus beta. H has the same dimension as the rank of our root system. And all G alpha, in our case, are one-dimensional. So this is our Lie algebra, and we have decomposed it in this way. Is this decomposition clear on the example? And do you understand that in fact alphas, these are linear functions on our Cartan subalgebra? In fact,
xi plus xj or xi minus xj, these are linear on H. If you sum up two elements of H, this stuff will also sum up. So you don't know what are the elements of this matrix. They can be all zero, but the two ones are 1 minus 1, for example. In this case, x1 plus x2 will be 0. But some on some subspaces, each non-zero matrix will be non-zero on some subspace. So in fact, these elements live in the dual space, and it coincides with this one. This is the same stuff. But now we do not see the formulas for alphas. Maybe a question for you. What if we take G alpha plus G minus alpha? Will it be what if we take a commutator of two vectors? Will they remain here or not? Будет ли это замкнуто относительно коммутатора?
And if we follow that formula, we should land in H, right? Scripting.
Yes. So this is if we take H, a vector x alpha, x minus alpha, and we take one-dimensional element from G0, x alpha, x minus alpha. This is a three-dimensional subspace, which will be a copy of SL2. To SL2. So in fact, every Lie algebra contains of many copies of SL2. And it is important if we want to classify them.
But we know SL2, but we do not know which dimension, yes.
It has dimension 3. So in each Lie algebra, you have many copies of subalgebras isomorphic to SL2. So for every two vectors alpha and minus alpha, you take their commutator. It will be a vector from from H. This is from H. And these three vectors will give you a copy of SL2. I didn't mention that this set, it satisfies all the axioms of the root systems.
what axioms do we have? That it contains minus alpha with each alpha, and that some numbers are integers. The second is more complicated. To explain this, we will need some representations. But all this stuff is held. And the very important theorem is that in fact there is a bijection between simple Lie algebras and indecomposable root systems. I have one more page. Bijection. So a pair of simple Lie algebra. Simple is such that it cannot be decomposed into the direct sum of two another Lie algebras. So every semi-simple Lie algebra is a direct sum of simple Lie algebras. Together with the Cartan algebra, it doesn't matter because all the Cartan algebras are conjugate, but we did not prove it. We didn't discuss it. And root systems together with the Euclidean space in which they live. Indecomposable. Do you remember what is indecomposable? Да. It can be decomposed as a direct sum of two root systems living in two orthogonal spaces. Yes. So in this direction is that we just look at the action of H and G and find the eigenspaces, and the corresponding eigenvalues will give us the root system. And in the other direction, it works with the structure constants. You just have some data from root system, and you want to construct vectors in G, and how to compute them. There are some numbers which come out. You calculate these numbers using all this stuff. So this works in both directions. For any root system, you can construct the corresponding Lie algebra. It is quite complicated for E6, E7, and E8, and it is very well known for classical root systems. I think I will stop here. Any questions?
But can you give a reference of this?
There are many references. Yes, sure. For today's lecture, this stuff about Lie groups was taken from Wilmer Kanishik. This is in Russian. There are many books in English, I suppose, the Grubaki, not the third one, but maybe the first or second one, which is written about Lie groups and Lie algebras. Any textbook in Lie groups and Lie algebras discusses this passage from a group to an algebra. And for the root systems related to Lie algebras, just open Humphreys. It is devoted to this. But also in Humphreys, they discuss not semi-simple Lie algebras. This part was omitted by me. I didn't want to deal with it. If you want on the simple Lie algebras, this is part 2. Part 2 is totally about simple Lie algebras. And part 3 was about root systems. We learned more or less part 3. Okay. Any other questions? Then thank you for your attention. Давай наступно же.